channel, and this is for the love of chemistry. Here we make chemistry simple, easy, exciting, and beautiful. Alright, you are so welcome. And today, without wasting much of your time, we are going to look at another use of titration. And if I am going to finish every use of titration and all the questions, we may never even finish titration and where we start. So I want to end with solving for water of crystallization. And I believe that at the end of this, you'll be able to tackle any question, even if it's not part of what I've already taught you. Alright, so we're going to look at determination of water of crystallization. Here the question says 1.75 grams of ethane dioic acid with X number of water molecules were dissolved in 250 cm cube of water. An average of 22.2 cm cube of the resulting solution completely neutralized 25 cm cube of 0.101 mole per dm cube of potassium hydroxide. Question number 1 says, write a balanced equation for the reaction. Alright, so when we look at this question, I have taken my time to teach you how to write a balanced chemical equation. And I believe that with that knowledge, we can have a head start. So the first thing about writing an equation is to know the reactants, because it is the reactants that will give you the product. You don't have a product manufactured from heaven or anywhere. It is what you reacted that will give you your product. So looking at this question, what are the reactants? It says ethane dioic acid was completely neutralized by potassium hydroxide. So this gives us that ethane dioic acid containing this X unknown number of water molecules and potassium hydroxide are the reactants. So for us to write a balanced chemical equation, the first thing we will do is to write our reactants. So we just copy this from here. Type ethane dioic acid. Always remember that your elements must be in capital letters. Plus potassium hydroxide. Now we know that if this is an acid, it is in aqueous solution. And this is, as we know, it's in aqueous solution because we are talking about the volume of the liquid drawn. So it's also aqueous. Now you remember that what makes an acid is the replaceable hydrogen ions present. If there is no replaceable hydrogen ion or replaceable hydroxonium ion, that compound or whatever it is cannot be an acid. So when we look at ethane dioic acid, we'll see that it has 2 replaceable hydrogen ions. Let me give you a structural formula of ethane dioic acid. It will make it a bit clearer. This actually looks like this. So I believe you've done organic chemistry and you know about organic acids. And this is the alkanoic acid group. This is what shows that that particular organic compound is an organic acid. Once you see this group, and you know that the hydrogen at the end of this is actually the replaceable hydrogen ion. So if we have 2 of these, that means that this is replaceable and this is also replaceable. So writing it in a normal molecular formula without showing the structural formula, it shows that we have two hydrogens here. But when you look at the structural formula, you will understand that the two hydrogens are actually replaceable. Let me give for example, if we have something like ethanoic acid. Now looking at this, even though we have 3 hydrogen atoms here plus 1 making it 4, there is only 1 replaceable hydrogen atom in this compound, because that is the one that is attached to the alkanoic acid group, the functional group of the compound. And functional group is actually the particular part of that compound that takes part in the real chemical reaction. So this functional group of this alkanoic acid is actually the COOH group. So it's only the hydrogen that is attached to this particular group that is replaceable. So when you look at this, you cannot say, we are going to have two, we are going to replace this and replace this. No, you're only replacing this. And let's assume that maybe this potassium hydroxide is reacting with this. You simply have potassium replace just that 1 hydrogen at the end of the reaction. So now, back to what I was talking about. So, but in this particular compound, the 2 hydrogens are attached to the alkanoic acid functional group. So they are both replaceable. That is why when these 2 react with themselves, you have this potassium replace this hydrogen. So very simple, when this replaces this, remember that when acid and alkali react, they form salt and water only. That doesn't change. Okay, so when this and this reacts, the metal here will replace the hydrogen here, just like it does in inorganic acids. Let me go with an example too. Let's say you have hydrochloric acid reacting with potassium hydroxide. What you usually see is potassium chloride, right? That means this potassium here replaces this hydrogen here. So in the same vein, the same way that potassium replaces the hydrogen in the inorganic acid, it is exactly the same way that the metal here will replace the replaceable hydrogen in the organic acid. And from the structural formula I showed you, you can see clearly that 2 of those hydrogens are replaceable. So we have that this will take the position of this to form an organic salt. Okay, so we have, when this replaces this, remember it is replacing 2. Let's still look at the organic formula. So when, please, these are capital letters, please. Capital letters. So when this replaces this, of course it will have K here and we also have K here. That means the same way we have 2 hydrogens here is the same way we have 2K. So K, capital K2, of course, with all this 2. So we have C2O4. Then plus, of course, the acid and the base reacting will give us salt and water. So we still have our water. But then we're not throwing this away, so we just bring it down. We don't know the number of the molecules of water attached. Even if we know, we'll still bring it down like this. You will just copy it down like this. You formed your salt and your water. Now you are just bringing this back to this place to keep it as part of the reaction. So that's the first step. You have written the correct equation for the reaction. And of course, this salt is still in an aqueous solution. Excuse me. This salt is in an aqueous solution. This is water, and this is still water. All right. So let's balance the equation. Now we have 2 hydrogen here. Considering this, it has been copied down, so we're not considering it because we don't know what this is. So we just copy it down like that. Okay. Now we have two hydrogen here, and we have, sorry, two hydrogen here and one hydrogen here, making three, but we have only two hydrogen here. And remember, whenever I want to balance equation, I always do what I call evening out. You know, balancing of equation is actually by trial and error. There is no particular method, but you do what works for you most. And for me, I like evening out because odd numbers will take you where you don't know. So seeing that this particular place has an odd number, I just want to put 2 to make it even. It's still by trial and error. So now that I have put 2 here to make it even, so I want to calculate my hydrogen now. I have 2 hydrogen and 2 hydrogen. That's making it 4 on the reactant side. And then I have just 2 here. So I can add 2 to make it 4. Are you following? Okay, so we have 2 carbon atoms here. We have 2 carbon atoms here. We have 4 oxygen atoms here plus 2 making 6. We have 4 oxygen atoms here plus 2 making 6. So that's balanced. Then let's look at this. We have 2 potassium atoms here. We have 2 potassium atoms here. And that's how you write a balanced chemical equation for the reaction. So that's question number 1 solved. All right.